Simbeor THZ is electromagnetic signal integrity software to design predictable PCB and packaging interconnects. And this is a tutorial on how to use Simbeor for post-layout analysis, for compliance analysis. Here I will demonstrate how to use Simbeor SI Compliance Analyzer. SI Compliance Analyzer has 4 different modes. And the first mode is electrical rule checking. Electrical rule checking is based on modeling of signal link to detect signal integrity defects, specifically reference integrity, impedance continuity, and it can be also used for preliminary crosstalk discovery. It uses two-dimensional field solver, Simbeor SFS, and fast electromagnetic wave models. So it allows interactive analysis of links in fraction of a second or thousand of links with automation. So let's get started. I open Simbeor and create new solution. And new solution I will create for this standard, which is QSGMII, standard 5 gigabit per second with I believe 30 picosecond rise time. Yeah, 30 picosecond rise time from 20 to 80%. So I create a solution, and solution specifically for this 5 gigabit per second, and by default it's 30 picosecond rise time. Analysis will run up to 14.4 gigahertz. Proceed with the solution and import PCB layout. There are options ODB++ or Allegro. I use ODB++ and select design, which is Open Compute Project, one of those boards here. And I also load stack up with slightly corrected stack up. And technology PCB should be packaged with PCB. Processing will be longer. Click import, and considering the stack up, we after every import we have to check the stack up structure. And I close Compliance Analyzer first and verify the materials. In this case, slightly corrected stack up, there was soda mask added, and soda mask dielectric should be properly selected. Right here it's just as in description of this board. So if I want to correct something, for instance, I want to add roughness model for conductors, I specify it here and do other correction, and then can simply export this new stack up into like with roughness. Example. So next time I will be able to use this one. So Simbeor open board view, and we gonna simulate those links, which is QSGMII. They're all over here. We can basically QSGMI, filter those, all of them here, select all of them and run ERC analysis for all of them. But some of them are not high speed, so we have to pick up the high speed. So to make process simpler, I hide all layers and select just top layer, and those are the links, and I put cursor on top of it. And we'll simulate those links in parallel and select specifically 8 links. And visibility can be adjusted over here just to make it more visible. And I use Control click. I select 8 links here. Show layers. Just to restrict the analysis to 32 port, I use Simbeor Verify license here. And the first type of analysis is electrical rule checking. Electrical rule checking is done for this specific data rate. And compliance conditions standard here, we request 2 stitching vias per each via, just to check this. We'll evaluate impedance to have it 100 ohm as in specifications, and evaluate crosstalk, let's say above 20 millivolts. This is compliance conditions. Also, to find the crosstalk, those are microstrip structures. The spacing quite large here, but crosstalk and microstrips may be even with a large spacing. So we'll increase the coupling distance and proximity here to 50 mil. And I also check the extract reference conductor for 3D view. And click run. So Simbeor uses fast analysis here. It will run analysis for 1117 cross sections first with a Simbeor SFS field solver. Next it will run analysis for via holes, and in just a second we will see that. And the analysis is done. In a moment it will render the information, all collected information such as crosstalk, impedances, and the crosstalk here evaluated in parallel line segments. And I switch to 3D view here. And the analysis is done with 1 volt step excitation and no losses accounted for in transmission line. So in reality this crosstalk is going to be smaller due to losses. And we can see some violations here, such as those bumpy rotas, discontinuities in reference plane. So to clearly see the discontinuities, we can restrict the number of layers to just those relevant here, and see that there are some cutouts under the whole thing here. Show layers. Also, we can see that impedance is really close to 50 ohm everywhere, green. This is scale for impedance, and those are places where crosstalk may come from. So it may come from some other line, so it's crosstalk discovery, so where it may come from, and what is the maximal value that you can expect at this particular location. Also, we can see exclamation signs, and they for via holes, and we can see additional information. What is the via, what is the impedance of via from top and bottom, at which frequency, what is the localization frequency, those vias, it's 16 gigahertz in this case. And just one stitching via found, so not many. So it's kind of, we can observe it, but then we need a report on how to fix it and so on. And this is the report generated by Simbeor. And in report, we can see all those vias with insufficient number of stitching vias. They basically have to be redesigned if necessary. No? But severity is low, so we can keep it like this. Reference discontinuities. There are critical places critical locations. So we can see that at some locations, and to see it more clearly, this is the location, and some of them are really critical, some of them marginally critical, I would say. This one is really critical. To make it more visible, we do like this. So we can see the metal was cut out around the vias and around the capacitors, and this is real discontinuity. So everything in this critical range has to be fixed first before even running the analysis for the structure. So impedance, there is not much impedance discontinuities here, all the severity low. So to remove this low severity warnings, collection of low severity violations can be turned off in the compliance analyzer. So to create report, I click save, and Simbeor will create a report of the whole thing, including everything, including law violations. So I switch again to 3D view, and I mentioned that the compliance conditions with low severity can be checked off. This is skip violation checkbox here, just to make report shorter. Report is written into this solution directory. If I open it, so I can see the report, all those bugs like reference discontinuities, the most critical bugs here. We can see the locations and so on. That's instruction to fix it. So after all critical bugs or critical violations are fixed, only after this, especially on reference integrity, this is important, we can go with fast signal integrity analysis, FSI. So it's a basic signal integrity analysis in time and frequency domain. It allows to evaluate more accurately crosstalk and traces, delays, skew, preliminary analysis of losses. If we don't pass on insertion loss, for instance, that's no way we can pass it with a more accurate 3D analysis. And it includes about 30 compliance metrics for signals up to 10 gigabit per second. It uses decomposition analysis with two-dimensional field solver for transmission lines and fast electromagnetic models of V. So again, this runs very fast, and hundreds of links can be analyzed with this type of analysis. So in Simbeor, all I need is just to switch this tab in SI Compliance Analyzer, Fast SI, and click Build, just to explain what it is. And before running the analysis, I need some compliance conditions. So how I'm going to tell what works and what not. Right here, Simbeor automatically attached some IOs to location on BJ side, on the other component side. So let's see. As I mentioned, there are about 30 different compliance metrics here, and for insertion loss, let's just define it in form of polyline. If I switch to document describing this compliance conditions, I can go to, this is reflection loss later, and this is insertion loss. Insertion loss is a polyline with points defined by horizontal frequency and vertical insertion loss. So I click edit polyline. It should be pass condition is above. The first point is 0.05 gigahertz minus 1. Second point is 0.5 minus 4. And third point is 5 minus 17.5. 5 minus 17.5. That's it. This is compliance conditions for insertion loss. For return loss, let's just check the return loss. And this is just flat up to frequency F1, which is 2.5. It's Nyquist frequency, and F2 is a baud rate frequency. And the formula above this, the formula is here. So we will use this formula. So to use this formula, we use equation, edit equation mask. Again, this you can put some meaningful name here, QS GMII5, for instance. Add row, and the first point is from 0.1 to 2.5. We can use 2.5, or we can use F Nyquist, and just parameterize it, as there is a hint over here, and the value is minus 8. And second is from Fn to Fb, 5 gigahertz, Fb, and the value is minus 8 plus 16.6 multiplied by log 10 F, which is frequency, divided by F Nyquist, 0.5 of baud rate here. That's it. This is our condition for reflection loss. We can also add conditions for power sum crosstalk and put it some simple condition below minus 30. That's crosstalk and frequency domain. See crosstalk tutorial and explanation what it is and how to use it. Crosstalk from pulse response. We can also put some simple mask minus 20 below 20 millivolts peak to peak. And what else? Let's check skew as well. Skew from single-ended TDT, and put very just for illustrative purpose, put very strict condition, 2 picosecond. It's definitely not required in this case, but we'll check how well aligned all those lines, traces, and so the only thing I need is extract or just run. I click run, and yeah, in the log file we can see that there was a linear network generated with a lot of models in here, and it's running. So while it's running, I explain other things in here. First, there is I/O configuration section here, where we can define, add I/O to pin model. It's package model or connector model can be added here in form of just capacitance, RLGC, package, or multiport. We can also apply direction of a signal, and we can also see every single I/O, how it is defined. For instance, where is I/O 1? The first Simbeor gets I/Os on logic component side, and the numeration is goes right here, and this is numeration of single-ended and differential. So it can be moved up and down here, just if you're not satisfied, but they appear in the order of selection of links, and first larger component side and then smaller component side. So side A, side B in terms of Simbeor. So we can see here this is side A, and side B is on the other side. So I close this, and while I was talking, Simbeor computed all those requested metrics. So I close this just to make more space, and take a look at each particular parameter. Insertion loss, and I can zoom in, zoom out, take the value. We can see we are way above the compliance metric. Return loss, I did double click, but I wanted to do this, and you can see this not even close, so it's very well optimized link. So I close it, no worries. TDR, we can pin those graphs and see them later if I want to experiment with losses, with vs, with adjustment of vs, which are extracted as parameterized objects into this multi-view section, and so on. Pulse, we can see crosstalk from pulse response. We can see that this is it shows just 23 millivolt, but this is peak to peak on rise time, fall time. This is fine crosstalk, microstrip. This is near crosstalk. You see my crosstalk tutorial for additional kind of information. And well, some of them passed. In crosstalk analysis, half volt pulse was used, and additional settings you can adjust this half volt to larger value in compliance conditions. Here there are some settings for time domain response parameters, and for pulse response, for instance, it's right here. So 1 volt magnitude in this case for pulse is half volt after 100 ohm termination. So how to get a snapshot view of this or report? Again, we have compliance browser, which can be used to collect all data from all simulations, collect and see them on one graph. For instance, this is insertion loss, and I use Alt 1 to remove the top and see all the insertion losses, all TDRs, Control A, and we can see some of them. Some of the links have some spikes over here, can be further investigated. Why is this so? But that's not bad. Overall impedance is pretty close to 100. Double click returns it. So power sum crosstalk is, you can see, failed. It touches over here. And pulse crosstalk, there are some failures. To investigate failures and skew passed, so we can see that the skew values, again, they okay, they're below 2 picosecond, so very well aligned. So to collect just failed, to be able to create a report, I click collect failed, and we failed only on crosstalk, and I can create report, save it, and report in this case is over here, solution 32 by default, and I open it, and again we can see okay, browser doesn't want We can see more information on, for instance, crosstalk from pulse response. We can see Vmax, Vmin. So the values basically of pulse, peak-to-peak value from pulse response, and some violations are high according to our goal. Okay, after we pass crosstalk. In this case, crosstalk was violated, but we set the goal not specified in the signaling standard, so it was just for demonstration purpose. Delay skew, preliminary analysis of losses passed, so we can put another metrics here, such as I diagram for I, but it basically doesn't matter already. Passed, everything passed. So we can proceed with 3D SI analysis. It's more accurate analysis of return losses, but pretty much the same as the 3D SI mode in SI Compliance Analyzer is based on advanced decompositional 3D electromagnetic analysis, and there are about 30 compliance metrics that can be specified in time and frequency domain. And there are presets for common SerDes standards. So I will show how to save load standard, and it uses again decomposition, a field solver for either two-dimensional field solver Simbeor SFS, or for transmission lines 3D electromagnetic solvers can be used, 3DML or 3DTF for packaging interconnect specifically. And it uses 3D full wave models for vehicles, most important, and for other discontinuities. Technically, it has unlimited data rates, but accuracy depends on geometry, material models, and localization. And we checked localization at the first step with ERC. In this case, localization is sufficient pretty much everywhere. There are a couple of violations, but we'll see how it goes. So let's go back into Simbeor. I close the compliance browser, and right here I have this preset done for compliance conditions for fast SI analysis. So and to reuse it, I just click 3D SI here, and it migrates the same compliance conditions here as we entered for fast SI analysis. So those conditions can be saved for further use in next time, just to avoid test. Okay. To avoid typing it every time, and during the automation as well, and the conditions can be loaded as well. So I can click load, and next time I'll save some time. So to run this analysis again, I just switch to 3DSI button here and click build. Simbeor again. Let me explain what Simbeor model look like, and first I probably can just run the analysis to make it faster. So I'll run, plot test parameters of discontinuity optional, and I put accuracy at lowest level for fast analysis, but in this case it's the accuracy is basically sufficient. And so okay, the license I am running in is Simbeor Verify, and this is not sufficient for. So again I go to Alt 1, yeah, and help, manage licenses, and pick up Simbeor complete license. This is the type of license required for this analysis. So again, I run the analysis. Oh, it's picked up it, and now it looks like it's running. Let me check. Job distributed job controller. No, it's not running. Let me just stop it and run it. Now it should run. Okay, job distributed job controller. I'm running it on a couple of computers, and this is all the discontinuity models here, including multi-views, identify and extracted. So in visibility, I can enable show transmission line, and that's how the model look like. So I double clicked. So there's some discontinuities here, and in the transmission line, coupled transmission line segments all the way. So that's where the most of this fine crosstalk comes from. And via holes or those BJ breakout areas. So some are identified as multi-vias here, and some are like discontinuity, general discontinuities that can be further optimized and so on. That vias, we can take a look at how vias look like. So all analysis, created analysis, they appear on the tree here in board analyzer section. So we can double click on multi-via and see the multi-vias. So this type of analysis is much more accurate comparing to FastSI. So FastSI uses fast model for via, but 3DSI uses extract the via geometry and uses in this case 3DML solver to solve extract scattering parameters of each via and discontinuity, and then it will automatically reunite them into this 32 port circuit. It looks like this, and check our compliance metrics, and we'll be able to create a report with more accurate models for vias and other discontinuities. So let's wait a few minutes and then we'll continue. So the simulation finished in about 20 minutes here, and we can see some boxes here are yellow, which is warning level, so it's not critical, but there are some critical, like skew. But skew was artificial condition, so just and skew on the other side. So we can create a report again with just passed or failed, collect, and this is what failed. File some crosstalk as in previous case, pretty much exactly the same. Pulse crosstalk also pretty much the same as in case of FastSI. So in case of skew, we've got larger skew here. So delay 1, delay 2, and we can see that the approximate via-hole models are not able to capture this skew, but with more accurate models we were able to capture skew up to almost 4 picosecond. So a few things here I have to mention. First, I use distributed computing, which comes with Simbeor complete network license only. So for acceleration, I used server. Second, because of low data rate, I didn't set up ports in IO configuration, so component port model automatic. But in case of high data rates, via port to component should be selected, or even T-line Z to component. In case of BGA or components like this with ball grid array, T-line Z to component is a good option for up to 100 gigahertz and higher. So we switch to auto here. Few other things is Simbeor created, if I switch to orthogonal view here, 2D, selectors around the each via hole separately and this part separately. So if you want to simulate effect of coupling, and especially in this case when stitching views are on the sides like this, so there is a manual option. You can remove those discontinuity selectors and add one big discontinuity selectors around them. This is manual work. Simbeor unite discontinuity selectors only if selectors overlap. So in this case they do not overlap, and right here there is option actually forced to create all selectors separately. For in some cases they very densely maybe overlapping. So another option here, if you create large discontinuity selector or simulate to very high data rate, so I can advise to use absorbing boundary conditions, this checkbox here. So that's increase reduce the simulation time, first of all, reduce the number of resonances at high frequency created by the boundary conditions, and overall is more accurate. Simbeor uses special case of absorbing boundary conditions, capacitive boundary conditions, specifically designed for PCB and packaging interconnect. One more thing is if you take a look at those multi-vias here, and this is multi-via 2, which we can see over here, and this is a parameterized object that basically with parameters defined over here. In this case there are large antipaths, and overall VA is highly inductive, and making those smaller, for instance, we can make it more capacitive, or moving those VAs closer together. It can be done in VA Analyzer, tuning, then such structure can be optimized. There are separate video on the Simbeor website. So finally I use Open Compute project board design. If you want to experiment with this, there is a knowledge base automation examples that include the original design in UDB or BRD format as well. So let's summarize the tutorial. What I demonstrated was multi-pass compliance validation. In multi-pass compliance validation, you first have to pass reference integrity checks and localization. In this case, VS will mostly localize up to 16 GHz, so moving it to higher frequencies make it hugely unpredictable, the analysis of any type. So you need to simulate the whole board to be able to predict it. So if this step passed, and it can be done in ERC, again with Simbeor Verify license, more accurate analysis of losses on VS can be done with SerDes SI, and specifically with SerDTF or SerDML also solver, where you can evaluate the dissipated power on each VIA and see more on this in recent DesignCon paper with Alex Manukovsky and his team from Intel on VIA design up to 100 and 120 gigahertz actually, how the localization evaluated. Second, you have to pass trace impedance continuity condition. It can be done with either ERC or fast SI. And this is important because of most of the reflections come from traces and from VS as well, but traces are the longer structures they can create. So all the impedance continuity, if you have, for instance, like 70 ohm or 130 ohm instead of 100, it's most likely you're not gonna pass the other conditions like reflection. Pass crosstalk and traces. This can be done in FSI mode. Again, this ERC and FSI is Simbeor Verify license. Crosstalk and VS, it requires 3D analysis. Closed VS that are close to each other can be united in one discontinuity selector. So if you don't pass crosstalk, there is no reason to pass to move into step 4. This is reflection loss and insertion loss, preliminary analysis or low data rate analysis can be done with FSI, and for high data rates and the final check 3D SI analysis is required. And then most of the standards, SerDes standards like Ethernet, OEF, and now GDEC, they are based on channel operating margin metrics, so that requires definitely 3D SI analysis. So this is the end of this tutorial. Thank you.